Hello everyone. Today we're going to continue talking about engines. Today we're going to dig into some nice gory kinematics about engines, specifically the crank slider mechanism. So we previously covered how to do position, velocity, acceleration, and force analysis for a crank slider in this course. Uh, what we're going to do is simplify it a little bit just for the engine case. So what we need to do is get rid of any offset, which in engines it's almost zero. And if it's not zero, it's close enough to zero that this math still works okay. So we're going to derive about as simple a model as we can get, and then we'll use it to look at some interesting things here later on by the end of the lecture. So this is our simplified model for a crank slider where we have no offset. We've got our crank here, we have our connecting rod here, we have our crank length R, we have our rod length L, we've got our crank angle theta, we've got this little defined angle phi in here, we've got this little thing Q, we've got this little thing S, we've got this little thing U there. So that's what we're going to define. So we've got two little right triangles there. So it's pretty easy to see that Q is going to be r sine theta, right? It's the opposite side of this triangle. That's also going to be L sine phi though, right? If I look at this triangle, it's the opposite side of that triangle. So you can forget about Q, but we're going to use this going forward. All right, so we're going to assume constant engine speed, which honestly it's not a bad assumption in engines because engines usually spin at high speed, and that speed doesn't change very quickly. So most of the effects are from an engine running at speed, not the speed changing. So I mean, there's an effect on the forces and accelerations, etc., for the angular acceleration of the crank. But it's going to be relatively small compared to just the forces required to sling the piston and connecting rod and crank around at higher constant engine speeds, near the max speed of the engine. So not a terrible assumption here. So for that, theta is omega times t for a constant angular velocity, so zero acceleration, zero alpha. We can go back to this equation here and we can rearrange it to get for the sine phi term. So I'm just going to divide through by L. S, that's the cosine component of that triangle, so it's the adjacent, so R cosine omega t. I went ahead and subbed theta for omega t here. U, that's the adjacent side for the right triangle on the right, so that's going to be L cosine phi. X, our piston position, which I didn't show in the diagram, probably should have. That's our piston position. That's the sum of S and U. So we just sum these two equations, right? And then we don't care about S and U anymore. Okay, cosine phi. I need to get rid of this in terms of the sine. So what I'm going to do is use that cosine squared plus sine squared is equal to 1. I'm going to rearrange that for just cosine, so it's square root of 1 minus sine squared phi. And I'm going to take that and sub it in right there. Sine squared phi, right? Sine phi we've already got an equation for, so I can take that and square it and put it in there. And then I can get this equation for x. This is in terms of r, L, omega, and t. It's great stuff I know, right? It's the crank length, which would be half the stroke. For the zero offset assumption, crank length r is going to be half the engine stroke. So you can find stroke, you can divide it by 2 and get r. L is connecting rod length, you can find that. You had to do it for a previous homework assignment. Omega is your constant engine speed in course radians per second. And then t is time. Take the derivative of this with respect to time, I get piston velocity. Again, it looks a little bad. It's not a bad derivative, right? Sines and cosines and powers, square roots and stuff. It's pretty easy derivatives, right? So just take your time. Don't make, don't do it 2 or 3 times and you'll get to the derivative. Differentiate again, and I get acceleration, right? But we've already can calculate these things, right? We've already can do piston velocity acceleration. We found d dot, and we found it for the more general case. So what's the value here? The value comes into some interesting things about the geometry of an engine, and specifically the rod ratio, which there's different ways of defining it. How we're going to define it is R over L. So that's going to be half the stroke divided by the connecting rod length is what we're going to define as rod ratio. So we're going to use binomial theorem to do an expansion of a series expansion of this equation, and you'll see why we do it in a second, so bear with me on the math here. So binomial theorem states that a plus b to the nth power is equal to this infinite sum here. And you know, if you're in this class, you already know, right? Or at some point in time, we're going to be able to neglect higher order terms. And so it's really what we want to know in this case is that in what situation can we neglect higher order terms? That's really where we're going to try to get here. So now I need to formulate something in this equation to look like the binomial theorem, otherwise I wouldn't have brought it up, right? So what are we doing? So we're going to take just this piece of it, and we're going to turn it into this form of a plus b to the nth power. So just to rearrange this a little bit, the square root's really just to the half power, right? So that's going to be our n. It's going to be 1/2. A is going to be this, and then b is going to be minus r over L sine omega times t, all that squared. Right? So if I set a, b, and n equal to this, then this part here that's in the box fits the binomial theorem. So what that means is this can be approximated by this term plus this term plus this term plus this term. And if I go forever, then it's an exact. But you know, obviously, we're going to truncate this series at some point in time. You know, we're engineers here, so when our answer is good enough, we're happy. Right? You know, scientists might not be happy with this, but us engineers, we're usually happy if we get, you know, once we get to the precision where we literally can't make it any more precise. You know, we're talking about inches. You know, once I get down to a tenth of an inch, or sorry, a thousandth of an inch, it starts to get hard to make. You know, once I get down to tenths of a thousandth of an inch, it gets really hard to make. So as long as I've got enough precision, you know, once to make something, you know, I don't need any more precision. You know, when I talk about things like, my brain just stopped working. Oh, factor of safety. When you start talking about factor of safety, you know, you put a factor of safety on some systems of, you know, 2, 3, 4. You know, it might be higher for some systems. For race cars, it might be closer to 1. But the reason you put a factor of safety on is because there's a lot of unknowns in systems. So, I mean, there's always a variability in engineering systems. So, you know, for a lot of the things we do, we don't need an insane amount of precision. So, you know, maybe somewhere out here, these terms out here, they're just not that important. So, let's look into this a little further. So I just went ahead and subbed these in here up to the binomial theorem expansion. I went ahead and solved this out for some of these terms. You'll see that this r squared over L squared, r to the fourth over L to the fourth, this stuff shows up and it's going to get bigger, right? R to the eighth over L to the eighth. So it's really just r over L squared, r over L to the fourth, right? So this r over L shows up in all these higher order terms, and if it is greater than 1, it's going to get bigger and be more of an effect, right? If it's less than 1, it's going to continuously get smaller, and at some point in time, not going to be a significant effect. As far as looking at some practical constraints on R over L, it can't be greater than 1. The crank length can't be greater than the connecting rod length, because then the piston would need to go beneath the crank. So we're talking about an engine where this would be the crank, this would be R, and then L would be this little short thing here, and the piston would be up here, and then the piston somehow ends up getting down. It doesn't work, right? Now, could you make some weird I don't know if you could make some weird theoretical engine. You're getting tricky geometry. It doesn't make any sense, and you know, if it's not mechanically impossible, it's mechanically very difficult, and there's no reason to do it. So it can't be greater than 1. It can't even really be equal to 1. So the case where it's equal to 1 would be like this, and here the piston would be up there, and that's fine, but then here the piston will be sitting right at the center line of the crank, and you got to have walls to guide this thing, and this crank is sweeping around. You know, could you figure out some weird kind of crazy offset along the z-axis engine to make this work? Sure. Should you? Or I don't even know. Sure, maybe. Is it a good idea? No. Just other than proving your dynamics instructor wrong, I don't know a good reason to do it. So you don't even really want it close to 1 for you know, reasonable, sane engine designs here. And really, there's no good reason you even want to be in that range. It's not like, sometimes you're limited by geometry or whatever from doing something you really want to do. In this case, we don't want to do this anyway, so the geometric limitations aren't a big deal, because for R over L around 1 to 2, we're going to have terrible transmission angles, and we're going to have really crazy angles of our connecting rod. So, we don't want it, right? That's going to cause huge side loading on our cylinder bores and all sorts of wear issues. It's just not good. So we don't even really want to be close to 1. So that's fine. A practical upper limit is somewhere around 1 to 3. That's where you find most engines, are somewhere in that 1 to 3 down to maybe 1 to 5 range. It doesn't go much past that. You start getting into needlessly long connecting rods when you start getting into the 1 over 5. There's just not a real advantage to have at some point in time, right? So at some point, this angle is fairly shallow, and there's no real advantage to be gained from changing this, because the change in angle is going to be very small, because we get into a sine and cosine type thing here. So the practical upper limit, somewhere around 1 over 3, and then it's going to be smaller than that for a lot of engines, or maybe significantly so. So let's plug in 1 over 3 into this expansion. You'll see that, obviously we can't neglect 1 here. That's pretty important. 1 over 18, and that's pretty small. But still, from engineering, we probably want to include that. 1 over 648. Now we're in 1 part in almost 1,000 relative to these other terms here. At this point, I can probably neglect that. If I just want an engineering answer, I'll be better than 1% accurate here. So again, for science, maybe this won't work. But for engineering and for what we'll talk about in a second, it's fine. We can lose this term, and we can especially lose these higher order terms, right? So we don't need to consider those from an engineering perspective. Again, there's going to be lots of other variations that are of a bigger order than any error from calculations on this term here. So for reasonable values of R over L, then we can approximate X as that. Using some identities and substitutions to make this a little easier, essentially we're just going to get rid of the sine squared. We're going to use an identity to replace the sine squared with a cosine. So when we do that, we can simplify it down to this. And here's where something interesting shows up here. So, we've got our R over L, right? We've got our crank length here. We've got our connecting rod length here. We've got our R over L showing up here. But note that we get 2, when we use trig identities to get rid of the sine squared in terms of cosine, we get cosine omega t and cosine 2 omega t here. So why that's interesting is that means that in the equation for position, we have something that looks like a pure cosine wave, but then there's this additional thing added to it at twice the running frequency of the engine that's going to change the shape of this curve, so it's not exactly a pure cosine. When I do the velocity, take the derivative of this, I get sine, and sine, again, twice the frequency. When I do the acceleration, which is where the forces are going to occur, I get the same thing, right? So I get a cosine, and then something happening at twice the engine speed. That's important, and I'll talk about why it's important here right now. So essentially what we've done, we've just kind of roundabout done a Fourier transform. I don't know if I'm pronouncing that correct. So, I'm from the Ozarks. It doesn't really, pronunciation's all over the place anyway. So, but anyway, we're doing a Fourier series expansion of this thing, which is essentially finding all of the, you're basically approximating a function as a whole bunch of sine waves at different frequencies. And that's really what we've done, right? We've approximated this thing as 2 components, one at one frequency and one at a frequency twice the primary frequency. So the higher order things here are called harmonics. And if you're I'm not a musician, but in the world of musical instruments, a harmonic is going to be something like like in a guitar, you'll pluck a string, and there'll be the primary frequency, which is based on the length of the string and its tension. In a perfect world, that would be the frequency that string would emit when it's plucked. But in a real instrument, then the vibrations from one string are going to get passed on to the other strings and cause those to sympathetically vibrate. The body of the guitar itself is going to change the frequencies, and what ends up happening is you get all of these other vibrations at different frequencies that are harmonics. And so that's what you're going to get in the engine case here is you've got an acceleration and hence a force that's going to occur at the frequency that the crank is running at. But then you're going to get this harmonic at twice the frequency. So what do I mean frequency on this? If you think about an engine at 3600 RPM, 3600 RPM, the frequency is going to be revolutions per minute, right? Divide that by 60 and I get 60 revolutions per second. I get 60 hertz. So the engine's going to be shaking it at 60 hertz. But there's also going to be a frequency, or there's also going to be a component of a vibration at twice that frequency as well. There's going to be one at 120 hertz. So what are these things? So the easiest way to think about it is, this one's really from the crank going up and down, which is at the frequency of the engine, and then this one's really at the connecting rod, accelerating back and forth. Because it's got to, if the connecting rod is stopped at the top, it's going to go down at the bottom and be stopped, and then it's going to accelerate again and be stopped up at the top. So the higher order things really have to do with the connecting rod. And then we see the R over L ratio here, which means that for smaller values of R over L, these harmonics become less of a deal, and our vibrations are more at the primary frequency of an engine. So, from a vibrational perspective, yeah, R over L being even smaller makes this even better and gets rid of the harmonics, and everything looks like more of a pure sine wave here. But there's a practical limit for that. For R over L, somewhere around 1 over 3. These two things are roughly 1, and this is going to have a magnitude of 1. This is going to have a relative magnitude of 1/3, right? So it's very significant, right? 30-some% of the total vibration would come just from this second term here. For 1 over 5, it's only 20%, but still very significant, right? So for any physically realizable normal value of R over L, you're still going to have the secondary component here. So this cosine omega t term is the primary, and this cosine 2 omega is the secondary in engine. So we have a primary, we have a secondary component that's at twice the engine speed. And again, do we have higher order terms? Yes. So in an engine, we'll have terms out here. But they're going to be higher frequencies, but the magnitudes are really small for reasonable values of R over L. So that's why if you've been around engines or engine balancing at all, you'll hear about primary and secondary. You won't really hear about tertiary at all. And maybe some OEMs care about that stuff. I don't know. But in general, for reasonable values of R over L, we really only care about the primary and secondary component. So that's what that means. The primary is the vibrations that occur at the frequency that the crank's operating at. The secondary is frequencies that are twice what the crank is running at. So when it comes to balancing, and we talk about, why is a V8 good? Why is a straight 6 good? Why is a 4-cylinder bad? Or, why, when we start talking about things like that, a lot of it gets back to how you can balance the primary and secondary components. And again, how you can do balance at the primary speed of the engine, at the speed of the crank's rotating, and how you can balance at twice the speed that the crank's rotating at. So some engines like V8s, like a cross-plane V8, I believe you get secondary balance. Primary you can do with really big counterweights, because primary imbalance is at the speed of the crank. So you can fix primary imbalance problems in most cases just by putting counterweights on the crank, because the crank spins at the crank speed. So you can counter those vibrations with something spinning at the crank speed, hence put weights on the crank. Secondary gets to be an issue. So for engines like some V10s, or like most V10s, all V10s, but anyway, V10s might have secondary imbalance problems. They're very common in V10s. I can't remember if it's all V10s. There's different kinds of V10s. There's split pin and shared pin, and but I know in a lot of V10s the secondary imbalance is a big problem. And for that you really need something spinning at twice the speed of the crank, and there's nothing in an engine spinning at twice the speed of the crank. The camshafts spin at half the speed of the crank. for a 4-stroke. There's nothing spinning it twice as fast. So either live with it, which in race car engines and lighter engines you might live with it, or you put a shaft that spins at twice the engine speed. That's a balance shaft. That's why you need a balance shaft for some engines, is if you have a secondary balance problem, you need a shaft that spins twice as fast as the crank. And the only way you can do that is literally gear a shaft or put chains on a shaft to have it spin twice as fast and put some eccentric weights on it. And it gets back to some engines are perfect primary and secondary. I mean, straight sixes are perfectly canceled primary and secondary, at least in this theoretical framework we have here. So they're naturally inherently balanced. So some engines are good, some engines are less good. We'll talk more about that next lecture. At low engine speed, none of this really matters. I mean, you can make a terribly, terribly balanced engine as long as you're running at a few hundred RPM and it's not particularly big. It just doesn't matter that much because the accelerations are so low. We start talking about 3,600 RPM, which is still a relatively low RPM for a modern engine. You know, for a diesel, it's not. But for like a gas car engine, this isn't that high, and you can see the acceleration starts to go bananas here. And then at 7,200 RPM, this is going to be 4 times higher than this because it goes up with omega squared. So, at some point in time, at some RPM, this becomes a serious situation. At some point, it will be a limiting factor in the engine survival. Okay, so that's just the acceleration of the piston and the connecting rod. That's just the acceleration of the piston. Actually, yeah, that's just the piston. That's not the connecting rod, right? Because this is just X. So this is just the acceleration of the piston. So again, this component comes from the geometry of the connecting rod, but it doesn't include the vibrations from the connecting rod itself. So and it doesn't include the gas force and gas torque either. So gas force, that's going to be the force from gas pressure on the piston. So that's the force in the pit cylinder times the area, or we take the pressure times the area. We get the force, I should say. So that's the gas force, and it's going to be pretty easy to calculate, right? It's the pressure times the area. Now you got to find the pressure, which is not going to be easy to calculate. So pressure's hard, area is easy. Area is just pi times the b squared over 4. And one thing I just remembered before I should go. So this x dot, if we're talking about forces, this would only be the force. So if we did this times the mass of the piston, that's going to give us essentially the component of vibrations only in way back here, only in this direction, right? We're not really talking about what's going on in this direction with the center mass of the connecting rod. So that would be another assumption in this, that we haven't really covered whether that's a good assumption or not. So, and I'll get into a little more on how to do a better job of this in the next lecture as well. All right, so back here, gas torque. So this would be the torque about the center line of the crank, the torque from the gas force at the center line of the crank. So that's going to be, it's not too bad. So that's going to be the component of the wall force. So that's going to be essentially this force comes from gas, pushes piston down, connecting rod is at some angle. So the connecting rod has to, because it's at an angle, there's got to be a sideways force component of that if we do a 2-force member approximation of it, which means there's going to be some side loading that results in the wall of the cylinder from this pressure here. So some of this pressure here, because the connecting rod's usually at an angle, that's going to result in some kind of a side loading on the wall of the cylinder. That side loading about the wall of the cylinder, about the crankshaft center line, that's going to give us torque. It's going to try to rotate the block. So this force here is just going to be the gas force times tangent phi. That gives us 1/4. That's 1 on 4. 3/4. That's going to be just from this little vector triangle here. We can find that. So that's just a little vector triangle where we've got the gas force minus negative the gas force minus FG14 here. So negative of that, negative of that. That's going to be FG34. we wanted that'd be the force on the from 3 on 4. So connecting rod on piston. So that'd be the wrist pin force. Torque from the gas, that's going to be FG. So the torque down here is going to be FG41 times X. It's going to be the side loading times X. If we flip the subscripts here, we get the equal and opposite here, and we get the torque. So this is 1 on 2. This is 2 on 1. 2 on 1 is what we want. 2 on 1 is the 2 on 1 is the force from the crank back onto the ground. That's going to be force FG14, which is 1 on 4, which we've already got. So we can take that and plug it in there. X, we've got an equation for that, right? Or at least an approximate form of that, and we can get an equation for gas torque here. So this would be the torque from the gas pressure here on the engine block. We've got a phi in here that we need to get rid of. So we've got an equation for finding phi from the geometry. So here we can approximate gas torque. We can get rid of some higher order terms and get a simplified form of this. So I went through that pretty quick and in not a lot of detail. So here's sort of the limitations of what we've done here. We've come up with some approximations, right? We've used a few approximations here, and we've used 2 force member assumption. We're not really considering the mass of the connecting rod, or don't really have any ability to do anything with offset eccentric weights on the crank. So we get some understanding on why R over L should be what it is, and why we only have to worry about, in general, primary and secondary vibrations, but we're losing some information here on these assumptions. So at this point in time, if you want to do a better job, rather than trying to keep refining on this approach, go back to force analysis for a crank slider engine and the equations we derived there, and you can use that to create a really good free body diagram based model where you can include anything you want to include. You can include the center of mass of the crank. You can include the center of mass of the crank rod. In fact, that's what you did in your project, right? So you can take what you did in the project and extend that for 0 degrees, 10 degrees, 20 degrees, or 1 degree or 10th degree increments, right? And you can make a total simulation of an engine that includes all the stuff that we're neglecting in this model. It includes the effect of the connecting rod center of mass. It includes the crank center of mass location. If we could put a model for force up here in the piston, and we could calculate reaction, the shaking torque, including the force from the piston, the gas pressure too, right? And we're not losing all the stuff we lose in this assumption. So there's a limitation to all models, and at this point we're sort of pushing this one a little too far. So I really like this part here where we start talking about just primary and secondary and why we only care about those. But again, to really do a better job or a good job of modeling forces, you're going to get back to what we've already covered in this class, which is multi-body force analysis for a crank slider. So we've already done a better job than this simulation can give us. This just gives us some mathematically interesting things. Some practical values on engines here. So I just made a quick table here, some common engines. So LS1, that's an engine family that GM started making, like 97 Corvette, I believe, was the first thing that went, and then it went to the F bodies, the Camaro and Firebird in 98. And it's in the, I don't know, 4th or 5th or 6th iteration, I can't remember now, because there's the LS2, the LS3, the LT1, LT2, LT3, and LT4. I think maybe there's an, I don't know, there's an LT4 is out now. So lots of generations of this thing. The same engine, the engine is very similar to these parameters. Some of them are a little different, but essentially the bore is just under 4 inches, the stroke is just over 3.5 inches. Rod length, just over 6. That gives us that R over L, which can stroke divided by 2. Divided by rod length, that's R over L. You'll see it is somewhat smaller than 1 over 3, right? Which we're talking about, but that R over L should be less than 1 over 3. Bore to stroke ratio, we haven't really talked a lot about. That shows up more in engine performance. You see bore over stroke. Usually the higher bore over stroke, the higher RPM and the higher power engine makes. Usually the lower bore over stroke, the lower RPM and the more torque an engine makes, generally speaking. And this engine's got a stock max RPM somewhere around 6,200 or so. It depends. This can be higher. You can usually spin engines past this to some amount. The Coyote, that is a V8, smaller displacement engine. So like, this was a 5.7 liter when it first came out, and they made a 7 liter variant. The 6.2 is real common. The Coyote, they make it a 5 and a 5.2 liter. Makes similar power. And it's got a smaller bore, which is smaller displacement. It's got a larger stroke, actually, and a shorter connecting rod. So here the R over L ratio is... yeah, so it's, well, it doesn't make a whole lot of sense. Yeah, sorry, stroke is longer. Sorry about that. If you'll notice, the values have magically changed because I realized that I had used the wrong column for the calculations in this, and the numbers didn't make any sense. So, if you look at this divided by 2 divided by rod length, you get R over L, the rod ratio. And though it's changed a little bit here, not a lot. What I was concerned about is that this number should go up, and it didn't in my original calculation, so I knew I'd made a mistake. I don't know how I didn't catch it before. I assume what I did the bore calculation, so I just fat fingered in Excel and grabbed the wrong column. So I went through and calculated these things real quickly. Glad I caught that before I published this on the internet. But I'm not going to delete my mistake because that's how you learn. Anyway, so R over L is less than the 0.333 for the 1 over 3. The Coyote, that is, it's funny in that this is regarded as an engine that spins at higher RPM, and it does in general. And it's dual overhead cam versus an overhead valve in this, and that's usually known for spinning at higher RPM. But it's actually got a worse rod ratio. And why? So Ford kind of did something I would consider to be dumb a long time ago in the early 90s. And they made their modular engine family and had a really short, small distance from bore to bore on the blocks. And it really limited how big of a piston you could put in there, how big the bore can be. And it really limited their displacement compared to what GM and other manufacturers at the time, V8 manufacturers. It was pretty well just Ford and GM were doing these kind of V8s at the time here in America. Chrysler had one, but they'd been using the same thing forever. Until recently, they're joined this game 10 years or so ago with their new Hemi. But anyway, back in this early 90s time frame, again, they really kind of shot themselves in the foot with the bore, and they've been trying to get every bit as much bore out of this same center to center distance as possible, and that's why they've had to use the really thin liners, or trying to go with no liners with a spray bore. It all goes back to a decision made back in the early 90s, whereas GM with their LS1 engines, they used a lot wider bore spacing and are able to get by with a bigger bore. Right, small changes in bore make big changes in area because it goes up with bore squared. So again, we're talking about maybe adding an inch of length to the engine would have made given Ford a huge amount of flexibility in their displacement. Now the upside of that is because they were limited by bore, they've had to do all sorts of fun things to make power. So they really spin these engines fast. 6500, this is the first generation Coyote. These things spin over 7,000 RPM. The 5.2 Voodoo engine that was a flat plane crank engine, which we'll talk about next time, that thing spins like 8,000 RPM. It's nuts. So that's how you replace displacement in a naturally aspirated engine, is you spin it faster and make it breathe better. So sort of as a result of their bore spacing choice, almost 30 years ago, they've really had to make these engines breathe really well and spin high. And they're great engines. I had a car with a Coyote, and I loved it. Sold it. I have diesel now, but it was a great engine, great car. So it's just a different way of solving the problem. But again, you kind of get stuck in here where it's acceptable, but you'll see that's actually the highest of all the ones in this table until we get down here, especially with the gas engines. The old school 426 Hemi had a nice R over L. These things will spin for big engines, right? The bore is big, but the stroke isn't that huge. So these things can actually spin high RPM. As long as the components can withstand it and the valve train has stability, they can spin pretty high RPM and make a ton of power. Nothing wrong with that at all. F1 V8s, so these things spin insane RPMs. The V8s are gone. but they're pushing 20,000 RPM, even higher. I've heard some numbers as high as 24,000. I don't know if I believe that or not, but 20,000 RPM. So in that case, all those higher order terms are going to start to be problematic. And even the secondary term, you really want to try to minimize it to try to keep these engines alive. So they have a very, very low value of R over L. This is something that was really wrong in that previous table I had. So this makes a lot more sense where the R over L is really small, closer to that 1 to 5 range. And that just gets rid of those higher order harmonics and it makes the secondary less of an issue. The Merlin, I just put it in here for historical purposes. I couldn't find rod length on it. The only number I found was 14 inches, and that seems too long. Maybe it's right. I don't know. That's probably overall length, not center to center length of the connecting rod. But you can see how much bigger of an engine it is than even like a 426 Hemi. The diesels here. So these are the three diesels that Ford, GM, and Ram, I guess, now put in their 3/4 ton and 1 ton trucks and some other trucks. So Cummins makes this engine, Chevy makes that, or GM makes the Duramax, and Ford makes the 6.7 Power Stroke now. And you'll see that these two have very similar rod ratios. The Cummins is actually the worst of the lot in that. For diesels, though, note the max RPM. It's not that big of a deal because they just don't spin that high of RPM. So it's not the secondary stuff. They're pretty harsh anyway, so honestly, it's sort of not a secondary consideration, right? It's not that much of an issue since they don't spin that high. I mean, we're less than half the RPM of these engines up here. So, what's the limit on RPM? It's how long it takes diesel fuel to burn. When you squirt the diesel fuel into the cylinder and it burns on the boundary of the droplets in the air. It just takes time for those droplets to burn, and it's really, even with that really high, almost 30 to 40,000 psi systems, still there's a limit for how quickly you can burn the fuel. Now these engines will usually be mechanically able to rev quite a bit higher than this. So I have a truck that's got the Duramax in it, and so when you're driving forward, yeah, it shifts somewhere in the low to mid 2,000 RPM is where it likes to shift. It really stops making power after 2,800 RPM. That's when really the pumping loss is. There's really a lot of flow restriction, even though it's got a turbocharger. It's really not sized to breathe in a lot more air than what the 400 horsepower or so it's rated at. But when you're going downhill and have the turbo brake on, it will actually downshift to 3,600 RPM, which is kind of interesting when you're used to being around 2,500 RPM, and then all of a sudden it downshifts to 3,600 RPM to engine brake. So like if you've got a big trailer, like have an 18,000 pound toy hauler trailer that going downhill, it can keep its speed really well because the aerodynamic drag on the trailer, but also because this engine braking, and it uses that extra RPM to create more pumping losses to create more braking. You'll see that the 6.7 pretty similar. Basically, they're very different. Or not very different. They're slightly different in the bore and stroke ratios here. The Duramax is very, very similar geometrically to an LS1, actually. I mean, they're not really the same at all. They're not based on the same platform, other than they're both V8s in the same displacement range. But the Duramax is at least shaped more like a gas engine, whereas the Power Stroke is shaped more like a diesel, where the stroke is longer than the bore here. But the rod ratio is still basically the same between these two. The Power Stroke has to have a 1/2 inch longer connecting rod, which makes the whole engine taller and physically larger. This is a newer engine too, so there might be some lessons learned from the Duramax and when Ford developed that engine. They had a couple, the 6 liter and 6.4 were fairly disastrous engines that they had to learn a lot of lessons from. The 6.7's got a pretty good reputation, other than the pump. The pump on these two engines is for some generations is a problem. The injection pump, that's a separate subject. 6.7 Cummins. This is an iteration of an engine like going back to the old 6BT, I think. The engine's been around a long time, but they've just gradually made bigger and better. It's a straight 6. These are both V8s here. This is a straight 6. And you'll see that it doesn't have a particularly good value for R over L. It's close to that 1/3. It's the worst of pretty well anything in this table here. So, low RPM, don't care a lot about the higher order vibrations because there's just not a lot of RPM. There's not a lot of acceleration just because there's not a lot of speed. But that's interesting. But what you see though is because there's only 6 cylinders for the same displacement, we've got bigger bores, so we've got a longer stroke, and we've got a really long connecting rod, and this gets to be a really tall engine. I mean, it's over an inch longer in that direction than the Duramax is. So it starts getting to be a really tall, skinny engine, and it's harder to fit in things than the V8s are. Yamaha R6 is a little motorcycle engine that I'm familiar with from a lot of projects. You can see a pretty big bore, pretty short stroke, more like the F1 engine. Rod length 3.56 inches. That gives an R over L really good, right? And again, high RPM. We really want this to be good. We want it to be low. That gets rid of it reduces our secondary vibration, and it helps the higher order frequencies too. You can see, humming around at 16,000 RPM or so. So anyway, that's a little bit on engines. We'll talk more about the different kinds, V8, 4-cylinder, V10, that kind of stuff next time. We'll talk about sound too next time. It should be a fun lecture next time. So that's it for today. Thank you.